Okay, so before we get to the next section of the course, which would be on cardiac MRI, I need to talk about some of the basics of MRI physics, uh, just to get the junior residents up to speed. So the objectives here are to discuss basic principles of signal generation with MRI, describe T1 and T2 and how it affects image contrast. We'll talk about the difference between spin echo and gradient echo pulse sequences and understand the basics of how MRI data is converted to image data. So when we're dealing with MRI, the signal basically comes from hydrogen nuclei. And we use electromagnetic radiation in the radio frequency range, and that range is non-ionizing. So if we look at the different types of radio frequencies that there are, so we're dealing down here in the range of wavelength sizes that are radio signals. So those are very large wavelengths, and so they have less energy compared to what we use for diagnostic imaging way over here, which has a very short wavelength and is much higher in energy. So this is ionizing radiation, and when we're dealing with MRI, it is non-ionizing radiation. So the idea is that we're going to apply radio frequency pulses to excite these hydrogen nuclei, and then we're going to get signal from these hydrogen nuclei, and that's going to depend on the environment that the nuclei are in, determines the amount of signal that we get, and we transform that into image data. So these nuclei, once they are excited by the radio frequency pulse, will emit energy as a radio frequency signal, and we call that an echo. The signal strength will depend on the pulse sequence and the local environment of the hydrogen nuclei. So here on a T1 weighted image where we have fat, we're going to get higher signal. Where you have myocardium, there you're going to get lower signal, and that's a characteristic of of what these nuclei are surrounded by, the types of tissue they're surrounded by. So we give a signal, we get an echo. The problem is deconstructing the signal to locations in three-dimensional space, because when we apply a radio frequency pulse and we get the signal back, we get the signal back from all of the tissue that was excited. So we have to be able to encode the signals so that we can derive three-dimensional spatial information from the signals to localize the areas of higher signal and the areas of lower signal, and to create these images. So here in the beginning, when you go through the textbooks, they go through these models of spinning protons and the longitudinal magnetization vectors and all of that. These are just classical models, and they have limitations. If you think about it too much, then parts of it will not make sense, but that's okay. It's enough to, for our understanding, for what we need to know. It's enough to get a basic grip on, what is going on, or to understand what is going on. So these hydrogen nuclei have a dipole moment, so you can think of them, since they're spinning charges here, as little magnets. So there's a part that points up and a part that points down. And when placed in a magnetic field, these will align either with the direction of the magnetic field or against the direction of the magnetic field. It turns out that it's almost very close to 50-50 in terms of those that align with compared to those that align against. But just a few more parts per million will align with the field. And whatever happens to those protons that are aligned with the field compared to those protons that are aligned against, they cancel each other out. But because of that difference of just a few more parts per million that are aligned with the field, that's what gives us the net signal that we get. That's responsible for the signals that we get from MR. So my first question to you is, why is a 3 Tesla magnet better than a 1.5 Tesla magnet? What's the difference?
It's more will align.
What?
More protons will align.
Yeah, so that difference in terms of those that align with compared to those that align against is also determined by the strength of the magnetic field that you apply. So having just a few more parts per million that are aligned with the field compared to those that against, what does that translate into?
From the signal.
Better signal to noise. Right. So that's why these higher field magnets will have better signal to noise than the lower field magnets. That's what makes the difference there. Now, the other thing that happens is we think in these classical models of these protons as spinning tops, but when we put them in the magnetic field, in addition to spinning, they start to precess. You see how they wobble around this axis, the direction of the main magnetic field. So that's called precession. But there's a frequency of that precession, and that precession is related to the strength of the magnetic field. And what is important there is that they will only absorb radiation frequency pulses at the resonant frequency, at the right frequency that aligns with the frequency of their precession. So you have to provide magnetic pulses at the right frequency in order to excite the protons given a certain precession rate. And that's going to allow us to pick or to select, where in the tissues we're going to excite the protons, and we'll talk about how we use gradients to do that. So the precession and the resonant frequency is determined by the magnetic field strength experienced by the nuclei. So what it comes down to is that this precession frequency of the nuclei is determined by the magnetic field strength that that particular nucleus experiences. So most of that magnetic field is from the main magnetic field itself, but there's some of it also that's determined by how this field is affected by the surrounding tissue. So the surrounding tissue may accentuate the field that it feels, that this proton experiences, and if it's increased by the surrounding tissue, added to the magnetic field, what happens to the resonant frequency? Up or down? If the magnetic field that this proton experiences is slightly greater than what is in the main magnetic field, then the frequency of precession will go up. Remember, that frequency of precession is related to the magnetic field strength that the proton itself experiences. If there's tissue around the proton that is shielding it from the main magnetic field, then what's going to happen to the resonant frequency? It will go down, right? And so the surrounding tissue also, in some sense, will determine what the field strength is that is experienced by the proton. So now we can also change the field strength that the proton experiences and its resonant frequency by manipulating gradients in the main magnetic field, and we can do that three-dimensionally, and that will help us eventually to encode, to provide this three-dimensional information within the signal that we receive, and that helps us to generate the images. So it's that gradient manipulation that allows us to get spatial localization and to generate images. And it's all goes down to the same basic thing, is that precession frequency or the resonant frequency of the proton is determined by the field strength that it itself experiences. Now, if we have a whole, let's pretend we have an imaging slice here. You have an imaging slice, you have a whole bunch of protons here within this, right? And they're all resonating and, assuming that they're all just feeling the same magnetic field strength. So they're all precessing at a certain rate, so that's what's depicted here. And we can think of, adding all these vectors up to getting a net longitudinal magnetization vector here that is aligned with the magnetic field. And then what we're going to do is, to simplify it and then not worry about the spinning and all, is that we're going to apply radio frequency pulses, and we can think of these radio frequency pulses as tipping this main magnetization vector over this way into the horizontal plane. And then that's what eventually is going to give us signal. So we have the main magnetization vector here, we're going to apply radio frequency pulses, and then that's going to tip it into the transverse plane. And so here we've depicted a 90-degree pulse. Here in this example, so you have all of these small protons with their dipole moments, and then the main magnetization vector here is depicted pointing up. So here it's showing you what happens with a 180-degree pulse. as we tip it into the transverse plane, and then it goes down all the way down to, flip all the way down to 180. So that's an example of what happens. So to simplify all of this, instead of thinking about each of these individually, we'll just deal with this longitudinal net magnetization vector, and we'll deal with that. And it's much easier to understand what is happening if we do that. So we'll start with a 90-degree pulse, and we'll tip that into the transverse plane, and then it will start precessing here in the transverse plane. And that 90-degree pulse is the best for generating signal, and we'll see why. So once it's flipped 90 degrees, it's still precessing. It's turning around, it's precessing in that transverse plane, and then we have a receiver coil. And since this represents some magnetic field here that is going through, as it's turning around, it's going through this receiver coil, it's changing the flux through that receiver coil, and that's going to generate signal in the receiver coil. And that signal resembles a sine wave. Why? Because this is rotating through, and you can see that as this rotates through, the signal increases and then it decreases. So you get a sine wave. And it decays. The signal decays, and we'll talk about why the signal decays. So this, by the way, this example here, where you just flip it 90 degrees and then get your signal and watch the signal decay, that's called free induction decay. That's the terminology for that. So the main reason why the signal decays is because of loss of phase coherence. We'll talk about what that means. Now, to avoid thinking about all this spinning and all this motion, the textbooks will talk about putting you in a rotational frame of reference, which means that you're in a frame of reference actually turning around with this transverse component, so that you don't have to worry about its actual spinning. You can just deal with the magnitude of this component as it forms when you flip it 90 degrees, and then as it decays, as it gets shorter and shorter. Okay? So that's the rotational frame of reference. And using that, then you can ignore the precession and focus mostly on the magnitude of this component. So talk about these terms of T1 and T2. So T1 relaxation, the other fancy term for that is spin lattice relaxation. And what that means is once you've applied this radio frequency pulse, you've taken this net longitudinal magnetization, you flipped it 90 degrees, but over time it's going to recover. It's going to go back to where it started. So that recovery of that longitudinal relaxation is related to T1. That is what T1 describes. So T1 is the time constant for longitudinal magnetization to recover to 63% of its initial value. That's what that number T1 means. So if I say that the T1 of a particular tissue is 100 milliseconds, that means it takes 100 milliseconds for this to recover to 63% of where it started. All right, so that's T1 relaxation. So fat has a short T1, water has a long T1, which means that the longitudinal relaxation for fat recovers shorter or faster than water in a shorter time period. Right, so it recovers faster. It takes water longer to recover this net longitudinal relaxation. Okay, so that's what T1 is. Now, the other thing that happens, though, is that once you flip this transverse component, as we've said, into the transverse plane, it precesses, generates signal in your receiver coil. The magnitude of the signal is determined by the transverse component. The signal resembles a sine wave, right? But it decays, so we've talked about all that. Now, the main thing, what is the main thing that causes that signal to decay? The main thing that causes the signal to decay is dephasing, loss of phase coherence. So if you think of all these tiny protons, that they're flipped 90 degrees and they start precessing, they all start in phase, but eventually they go out of phase fairly quickly. And when they go out of phase, then you lose this coherence, this phase coherence, and that causes that signal to decay. So that dephasing, there are two main effects that cause dephasing. One is called the intrinsic T2 effect, which is not reversible. And that intrinsic T2 effect, you can think of that as determined by the environment of the proton itself, by the type of tissue it is surrounded by. And that's good for us because that's essentially what we want to do. When we look at these signals, we want them to correspond to different tissue types, pathology versus normal tissue. So that decay, think of that as the intrinsic T2 effect. But there's also decay because of extrinsic magnetic field inhomogeneity. What does that mean? That means that the magnetic field itself, the magnet, is not perfect. There are slight differences in very close locations of the magnetic field that the proton experiences just because of inhomogeneities in the magnet. And ideally, you want to get rid of that so that what you're looking at is determined by the tissue environment of the proton itself and not inhomogeneities in the magnet. And fortunately, there is a way to reverse that. So that cause of dephasing is reversible. So the intrinsic T2 effect, spin-spin relaxation, we've said that that is not reversible. And when we say T2, so T2 is the time constant for transverse relaxation and dephasing, okay, from that effect, from that intrinsic T2 effect. And it's defined by the time to decrease that signal to 37% of its initial value, right? So we flip it 90 degrees. If we're able to reverse that extrinsic effect, how long does it take for that tissue to get back for that signal to go down to 37% of its initial value? That's the T2 time constant. Water has a long T2, right? T2 time, that T2 time constant will always be shorter than the T1 time constant. So most the main contributing factor to why you lose signal will be that T2 time constant. And that extrinsic, that static magnetic field inhomogeneities, that we can reverse. Now, if we look at signal decay from intrinsic plus the extrinsic effects, which is what happens when you have free induction decay, when you just flip it 90 degrees, going back to this, right? That's called T2 star decay, because that's both factors. That's involving both the intrinsic effect, which is best for us for determining tissue types, plus the extrinsic effect of magnetic field inhomogeneities. So that's T2 star, the decay of that type of signal. So intrinsic plus extrinsic effects, that gives you T2 star. We prefer to evaluate the intrinsic T2 effect since that's determined by the tissue environments of the protons, and that gives us more information about pathology. So to be able to do that, we need to be able to reverse the extrinsic effects, okay? So if you were looking at only the T2 relaxation, the extrinsic effect, right, it would take longer for that signal to decay if you're able to do that. Whereas if you're combining both the intrinsic and extrinsic effects, that signal decays much faster. But we want to look at this, that T2 relaxation only determined by the intrinsic effect and not this, which is both the intrinsic and the extrinsic effects. So let's go through some definitions first. So the term TR, repetition time. So that is the time between radio frequency excitation pulses. So on a pulse diagram, this is usually what the excitation pulse, how that is depicted. All right, so that's your radio frequency pulse there. Here's another one. Here's another one. The time between these excitation pulses, that's called the TR. The TE is the echo time. It's the time from the center of the radio frequency pulse to the center of the echo. And TR and TE are measured in milliseconds. Now, one other thing that's important is that the pulse sequences that we use for imaging are designed to produce echo or signal at the selected TE. So notice that when we're doing free induction decay, as in these examples, you're getting signal throughout, right? But the way pulse sequences are designed when we do imaging is to get signal at a particular point in time, and that is the TE. And then it's very easy to measure for your electronics. Everything is set to measure the signal at the TE, and the pulse sequence is designed to produce signal at a pre-selected TE at the echo time. So how do we reverse those extrinsic effects? Well, that's done by what's called a 180-degree refocusing pulse, and that's going to reverse the magnetic field inhomogeneity. So how does that work? So we give a 90-degree pulse, all of this starts to dephase, and let's say it's going out of phase because of these extrinsic effects. So some of these get ahead, some of these protons get ahead in this transverse plane of these protons that lag behind. So you can think of this as racers on a racetrack, running around the racetrack. Some of these get ahead of the others that are behind. Well, if we apply a 180-degree pulse along this axis and flip these over on the other side and flip the faster ones behind, flip the slower ones in front, as you see here after a 180-degree flip. So if we do that to racers on a racetrack, essentially reversing the positions, the ones in front now go to the same distance as they are in front, but they go behind, and the ones that are behind go in front. And then we keep going, the faster ones catch up to the slower ones, and then everything is in phase again. Okay? So that is called a 180-degree refocusing pulse, and that will reverse the magnetic field inhomogeneities. It's not going to reverse those intrinsic T2 effects, but it will reverse the magnetic field inhomogeneities, and it will give us a signal out here. So the 180-degree pulse is put halfway between the 90-degree pulse and where you want TE to be, where that TE, that time to echo time. So that sets the echo time. Twice the distance from, so TE over 2, the distance from the 90-degree pulse and the 180-degree pulse, right? That's halfway to the echo time. And then once you give the 180-degree pulse, that determines where the echo time is going to be. That's how it's set. So the spin echo sequences, so what I'm describing is a spin echo sequence, uses these 180-degree refocusing pulses. That's what makes it a spin echo sequence. All right, so here it's depicted in this diagram, 90-degree pulse, things start to dephase, give 180-degree, flip it back, and then right over here we get an echo as the faster ones catch up to the slower ones, and everything is in phase again, and now you have a signal. So that diagrammatically here, this illustration is what we get with spin echo imaging. Okay? All right. So your first pulse is a 90-degree pulse. Your second pulse is a 180-degree pulse, and then we have our spin echo over here. So how do you change the TE in a spin echo sequence? Let's say I did a sequence where my TE was 100, but I want to repeat the sequence and I want to make my TE 200. How do I change that? You tell the tech sets it, puts it in, puts those numbers in there, and the software does it for you. But what is it doing? What's it doing?
Split the refocusing pulse up.
Yeah, it's moving the refocusing pulse, right? So where you put that 180-degree refocusing pulse determines where the echo forms in your spin echo sequence. And that's how you manipulate the TE in a spin echo sequence. Okay? So that placement of 180-degree pulse at TE over 2 determines the TE. You don't have to memorize these, but just to give you an example, what are these numbers T1 and T2? What are we talking about? We're talking about water. So the T1, this is in milliseconds, it's 4 seconds. The T2 is 2 seconds, right? Compared to gray matter, liver, fat. So look how short T1 is for fat. How short T1 is for fat compared to water. T1 and T2, much shorter for fat than for water. Okay? So if we do a T1 weighted sequence where we're going to take advantage of this, that's going to make fat bright. If we do a T2 weighted sequence where tissues with a long T2 are going to be bright, that's going to make water bright. Okay? So different tissues have different T1s and T2s, and by setting up your sequences to take advantage of that, you can bring out the signal characteristics of these different tissues. Okay? So concerning a spin echo sequence in MRI, which of the following is true? D, right, good. So you're paying attention. 180-degree pulse should come at TE over 2. Okay? All right, so let's talk about T1 and T2 tissue contrast with MRI. So we've gone through this. We know what TR is. We know what TE is, right? So TR and TE are measured in milliseconds. Hopefully you remember that. So what do we mean by T1 weighted imaging? So T1, this is easy to remember. T1 weighted image has a short TR and a short TE. That short TR accentuates the T1 effect. The short TE minimizes the T2 effect. So what's going on here? So imagine that, so we start out with everything in this, the net magnetization. So we're comparing fat and water. So everything is aligned with the magnetic field here. We give a 90-degree pulse, so that fat flips 90 degrees. Whatever is, made up of water also flips 90 degrees. Okay. And then over time, the fat is going to recover, and the water is going to recover to back where it started. But if your TR is short enough, right, the fat, more of that fat signal recovers than the water signal. So the second time I give a 90-degree pulse, I have more longitudinal magnetization from fat than I have from water that I can flip into the transverse plane. And when we give a 90-degree pulse, we flip that into the transverse plane. And now, what's going on here? Get rid of that. Okay, so we flip that into the transverse plane. And if my TE is short, not allowing for dephasing, right? My TE is short, then I'm going to get much more signal from fat than I will from water. If my TE is too long, then the fat will dephase and will not give me signal. But if my TE is short, I don't allow for the dephasing, so I will now get more signal from fat than I do from water. That's the principle of a T1 weighted sequence. That's how we get T1 contrast. So the fat gives me more signal, so you see the subcutaneous fat here is bright. The water gives me less signal, so you can see the CSF is very dark. All right? So that's a T1 weighted sequence. T2 is also easy. What is T2? Long TR, long TE. Okay? That long TR will minimize the T1 effect. The long TE accentuates the T2 effect. So what does this mean? So if I have a long TR, the distance from my last 90-degree pulse to my next 90-degree pulse, all of this longitudinal magnetization has recovered. So let's compare again fat and water. So all of that has recovered, okay? And now we're going to give a 90-degree pulse, and we're going to flip that into the transverse plane, right? So here's fat, flip to the transverse plane, here's water. But our TE is long. Because our TE is long, we allow then tissues that dephase very quickly to dephase. So those tissues have a short T2, but tissues like water that have a long T2, it's going to take that longer to dephase. So when I get out here to my long TE, I'm going to have more signal from the water than I will from the fat, okay? Or from brain tissue, let's say. So here, the CSF is very bright, brain tissue is much darker. Right? So why are T2 weighted? Now you'll notice if you look at MR images, you'll notice that T2 weighted images are noisier than T1 weighted images. Why is that? You'll notice that your T2 weighted images look very grainy compared to T1 weighted images. Why are T2 weighted images noisier?
So you allow more dephasing?
Yeah, because you have a long TE, right? You have a long TE that does allow more dephasing, and that loses signal, right? Even though the net signal of the water is going to be more than the signal of the other tissues, that long TE has allowed for dephasing of signal. So you have less signal to noise when you lengthen out the TE. So you'll notice on your images that you're looking for stuff that's bright, so that helps you, right? That tissue contrast helps you that it's bright on your T2 weighted images. But you'll notice that T2 weighted images are noisier than T1 weighted images. Okay. Although they probably have more contrast, especially if you're looking at pathology, because the pathology is going to be bright. So what happens in MR imaging? So we've talked about short TR, short TE. We talked about long TR, long TE. What happens if TR is long, but TE is short?
You get less contrast.
Yeah. That maximizes the signal from all of your tissues, right? And so that minimizes tissue contrast. Although it's very high in signal, it minimizes tissue contrast because you're not really accentuating T1 effects or T2 effects, okay? So your tissue contrast will be degraded. So we used to call these proton density images or spin density images. So long TR, short TE images, this is kind of what they look like. You see, there isn't much contrast between CSF and brain tissue, but there's a lot of signal in these images, okay? So if you have a long TR, all of your longitudinal magnetization has recovered, right? You give a 90-degree pulse. Now, the soft tissue in the water, flip that into the 90-degree, into the transverse plane, but your TE is very short, so you're going to get lots of signal now from soft tissue, lots of signal from the water. So the T1 or the T2 of the tissue doesn't matter here. You're going to get signal from all kinds of tissue, and so the contrast will be degraded, although it will be very rich in signal. Your image will be very rich in signal. Okay? Not much tissue contrast. Why don't we do short TR, long TE imaging? What's going to happen with short TR, long TE imaging?
Low signal from everything.
Yeah, it's going to be low signal overall, okay? Because with that short TR, long T imaging, that long T imaging is going to allow for lots of dephasing in your signal. So whatever you were trying to accentuate from T1 effects using a short TR is going to be dissipated by the long TE. Okay, so it's not a very good pulse sequence for signal to noise or for differentiating tissue contrast. Okay, so your basic spin echo sequence, so your pulse diagram, 90-degree pulse, 180-degree pulse, you have a spin echo, then we'll talk about these a little bit later on. There's a slice selection gradient, a frequency gradient called a Reed gradient, and a phase encoding gradient. But the pulse sequence itself, the ones that we use for imaging, are designed to produce an echo signal at the selected TE. Okay, so you're not getting signal throughout the pulse sequence. The pulse sequence itself is designed to give you your signal, to give you the echo at your pre-selected TE, wherever that is, and then that's where you get the signal. Okay. So now, so far we've talked about spin echo imaging. There's another type of image sequence, and this is called gradient echo sequences. And so instead of flipping it 90 degrees, we do partial flip angle, less than 90 degrees, right? Remember, it's the transverse component of that net longitudinal magnetization that's responsible for the signal. So even if we flip this only 30 degrees, that transverse component of that still provides 50% of the total available signal. So even with a 30-degree flip angle, you're still going to get some sufficient signal there from the tissues that you can measure. So the magnitude of that signal is determined by the transverse component of the vector. Now this allows for very rapid imaging because there's still going to be, between your TRs, if you make your TR short, there's still going to be some recovery, some longitudinal recovery. So you can use very short TRs in these types of imaging sequences, and you'll see as we continue that the TRs are going to determine how long your imaging sequence is going to take to eventually generate an image. How long does that patient have to sit still in the magnet for any given pulse sequence until you have an image? Most of that's going to be determined by the TR. So this gradient echo sequences allow for very rapid imaging, very short TRs. Some longitudinal magnetization is always available to generate signal. There is no 180-degree refocusing pulse. that also, that 180-degree refocusing pulse also contributes to time. That can set a limit in terms of how short you can make your TRs if you're using 180-degree pulses. But if you're not using them, now you can make your TRs very, very short, and then you can do very rapid imaging. So how do we change this? So we've said when we do spin echo imaging, to determine the TE, we determine that by where we place the focusing pulse in spin echo imaging, where we put the 180-degree pulse, right? How do we change, and this is a more advanced question, how do we change the TE in a gradient echo sequence? What determines the TE of a gradient echo sequence? Anybody's taking physics, studying for boards?
Is the flipping?
What?
Is the flipping?
Can't hear you.
Is the flipping?
No, what's the gradient that we use that changes the TE in a gradient echo sequence? It's the Reed gradient. Is that familiar to you guys? The frequency encoding gradient, the Reed gradient. So the Reed gradient here has a dephasing and a rephasing component. That's the frequency encoding gradient. So there's a dephasing component and a rephasing component that balances. And then right there, right in the middle of that rephasing component of the frequency encoding gradient, it's called the Reed gradient for that reason, is that will determine where this falls, determines where the TE is going to be. So moving this closer or further away manipulates where the echo falls. That's called the Reed gradient, the frequency encoding gradient. Is that familiar to you guys?
Is that also in a spin echo though? Or does that fall in the same place where the 180 is?
Well, the spin echo is determined by the 180-degree refocusing pulse, right?
Right.
So you'd have to use this properly so it doesn't counteract that. All of your gradients will cause dephasing. That's why I don't want to get out into the weeds, but all of your gradients cause dephasing. All the gradients that you apply to provide the 3D information will cause dephasing and loss of signal, and they have to be reversed in order to recover that. Okay, and so that's why you'll see that the polarities are reversed in some of these gradients. Okay, to be able to recover the dephasing that is caused by the gradient, to both encode it and also not dephase it too much that you lose all your signal. But yeah, your Reed gradient when you're doing spin echo imaging also has to be properly placed so it doesn't counteract the gradient. But it's the rephasing component here, right, that's going to determine when your TE falls.
What is a gradient?
We're going to talk about that.
Okay.
So the gradient is it's going to fluctuate the magnetic field that the proton experiences, but we'll talk about that. So these gradient echo sequences, the downside of gradient echo sequences is it's sensitive to T2 star since we're not using a 180-degree refocusing pulse. So it's going to be sensitive to both intrinsic and extrinsic decay, right? And not just the intrinsic T2 of the tissue itself. So when we talk about gradient echo sequences, it's sensitive to T2 star, intrinsic T2 effects plus the extrinsic T2 effects. So even though it's more of a kind of, you can make them T2 weighted images, realize that, they're not strictly T2, that it also depends on these extrinsic effects, also determines the signal strength. So there's a dephasing and a rephasing component of the Reed gradient that will determine that sets when we get the echo signal there. Now, how do we convert all of this to images? So we manipulate gradients to spatially encode the signals, okay? So we have a main magnetic coil, main magnetic field along the z-axis or the B0 field. So when we're putting the patient in the tunnel, that field goes in that direction. That main magnetic field is in the direction of the table. So that's where the protons will either align with or against it. And then we have transmitter coils that are going to provide radio frequency pulses, and we have receiver coils that are going to receive the signal. Okay? And then we have gradient coils. So these gradient coils are going to be able to change the main magnetic field that the proton experiences in different directions. So we have gradient coils that will change the field in the X direction or the Y direction in the transverse plane, and also in the z direction, in the direction of the table. And this will add to the main magnetic field, to that B0 field. And the noise that you hear in MRI is because as you start manipulating these gradient coils, it gets noisy, right? So it's these coils that produce that sound in imaging that makes the magnet so noisy. Okay, so we're going to add a little bit or take away a little bit to the main magnetic field in three directions, in the X, Y, and Z direction, with these gradient coils, and that's what's going to allow us to spatially encode the signal to get three-dimensional information from the signal itself. Okay? The cardiac coil, the fancy term for this, is a multi-channel transmit receiver phased array coil. That's what it looks like with the patient. Gee, I wish we had a window that looked like that. Okay. So let's starting with this three-dimensional information. Let's start with slice selection. How do you select the slice? If we just want to excite the protons within a particular slice, right? How do we do that? Remember that the radio frequency pulse excites protons at the corresponding precession frequency, right? So the precession frequency of the proton determines what frequency of radio frequency pulse will excite those protons. So we want to match that to excite the protons that, in our particular selected imaging slice. So there's a slice selection gradient. So what this slice selection gradient does is, in this example, so we apply a gradient along the direction of the table here, so here's the main magnetic field. So down here at the feet, the proton experiences a magnetic field that is less than what it will feel up here towards the head. So the main magnetic field here, by applying this slice selection gradient, it's more up here and it's less down here, right? And then let's say we have this particular slice in here, and we want to excite the protons in this particular slice, right? Then what we can do is we apply a radio frequency pulse in a limited range of frequencies that match the frequencies, the resonant frequencies of the protons of this imaging slice. Okay? And that's how we select a particular slice to excite. The slice thickness can be adjusted by changing the bandwidth. The bandwidth is the range of frequencies of the excitation pulse. Right? So if my excitation pulse has a very narrow range of frequencies, right, then that narrows the thickness of the slice that is excited. If I increase the range of frequencies in my excitation pulse, right, to cover frequencies, let's say from here to here, then I have made my slice thicker. How else can you change the slice thickness?
Change the gradient.
Yeah, if you change the strength of this gradient, right? If you don't change the frequency here, right? By changing the strength of this gradient, you can also affect the slice thickness. If you make this steeper, you're going to make the slices thinner, right? If you make this less steep, you're going to make the slices thicker. Okay, but usually slice thickness is changed by changing the bandwidth of the radio frequency pulse. Right? So that's how we select a particular slice to excite. Okay, so now we have a slice of tissue that we're able to excite. But the problem is that the MR signal that we get, assuming that we've picked this particular slice and we've excited only the protons in that slice and only the protons in that slice, that's the signal we're going to receive. The problem is that the echoes come simultaneously from all of the protons in that imaging slice, everything all together. But we need to be able to deconstruct that signal into individual pixels within the slice. Remember, the signal is coming from everything in the slice. How do we get the spatial information from the slice itself? 90 degrees, so this is a spin echo sequence signal. Okay, so how are these related? All right, so let's pretend that, we have all these violinists here, and each one of these is a pixel, right? And so the conductor provides the radio frequency pulse, the baton goes down, they play, right? So what we're trying to determine is how loud is each violinist playing. That's the amplitude of the signal, okay? The problem is all of these violinists in this imaging slice are playing at the same time, right? So how do we deconstruct that combined signal to get spatial information from all of these coming at the same time? Okay. So what we're trying to do is determine the amplitude of each pixel. That determines the brightness, right, of each pixel. That's the amplitude. But we want to be able to get the spatial information in our imaging slice to be able to do that. So here I've just put in these numbers. So pretend this is the amplitude. How loud is this violinist playing, right? Each of these violinists, they're playing at a different amplitude, at a different loudness. So this one here that corresponds to fat is playing very loud. This one over here, not playing as loud. The signal is lower, right? So they're all playing at the same time. We want to determine how loud is each violinist playing. We need to determine the amplitude of each pixel, which determines the brightness of the image. How are we going to do that? We do that with what's called Fourier transformation. So you have a complex signal here, which is the sum of the signals of everybody playing at the same time. This is what you get together. And with Fourier transformation, what you're doing is this says that you can break this down into a set of sine waves, right? Remember that each one of these is a separate sine wave. And you can take the complex signal and we can break it down into series of sine waves, and these sine waves, if we can get spatial information in here, that will determine the amplitude of each of the pixels in our imaging slice. So that's Fourier transformation. How are we going to do that? Well, first we must be able to spatially encode the signal. And the easiest way to understand that is the frequency encoding gradient, frequency this way. So what if I take, I have 3 columns of violinists here in my imaging slice. I will tell each violinist, play a different note. You play C, you play D, you play E. Your amplitude doesn't change, but the frequency of the note is different, right? So I now have 3 different notes, and I can hear 3 different notes, and I can break that down into the combined amplitude of all 3 different notes, okay? That's frequency encoding. And that's part of Fourier transformation. So some of you may remember this from lectures. Who's the best human at Fourier transformation in history? All right, take a guess. No, he was good. Mozart was. Mozart could listen to a whole piece. He'd listen to the piece, he'd go to a concert, listen to the piece, and he would write down what each part was playing, what the violinists were playing, what the cellists were playing. And then he would send letters to his father. I had this great piece the other night. This is what it was. He would write it down and say. So he was taking the complex signal from the orchestra, Fourier transforming it into all the different parts that everybody was playing, and write that down. That's Fourier transformation on steroids. Okay? So we can do frequency encoding. So we're able to break down the columns. How do we break down the rows? That is called phase encoding. That's something that human violinists can't do, but you can do it when we do it on the magnet. So we'll talk about how we do that. Okay. So let's start with frequency encoding. So these are the amplitudes that each violinist is playing. And if each violinist is playing a different note, I can break down the frequencies into this frequency in this column, the frequency in this column, and the frequency in this column. But the problem is I still have the net amplitude of this column to deal with, the net amplitude of this column and the same here. So what is the total amplitude of the first column? 3.5, right. So the note C gives me a total amplitude of 3.5. The note D gives me a total amplitude of 6. The note E gives me a total amplitude of 6. So I'm able to break down the frequencies into total amplitudes for the columns, but I'm still left with trying to get the spatial information from the rows. How do I break that down? Okay. And that is done by what is called phase encoding. Now, humans can't do this, but we can do this on the magnet itself, right? So I have two violinists here in a column, A and B. This one has an amplitude of 1. This one has an amplitude of 0.5, okay? If they are completely in phase, if the frequencies and they're playing the same note, if they're completely in phase, that's a 0 phase encoding gradient, okay? That's 0 phase encoding. Your total signal is 1.5. So A plus B equals 1.5. No problem there, right? Now, what if I'm able to tell them to play exactly 180 degree out of phase? If they play 180 degree out of phase, the signals start to cancel. So the total signal is now 0.5. It's A minus B, 0.5, okay? So I have A plus B, 1.5. I have A minus B, 0.5, two simultaneous equations, two variables. I can solve this. Now I know the amplitude of A and I know the amplitude of B. That is phase encoding. Okay, that's how phase encoding works. Now you'll notice that the number of phase encoding steps is determined by the number of voxels along your phase encoding axis. So if I had 20, I would have to do 20 phase encoding steps. And each phase encoding step requires sampling from one echo, right? Each of these steps requires an echo, right? So if I have 2 voxels in the phase encoding direction, that's 2 echoes. If I have 256, that's 256 echoes, okay? So far we have this. The MR signal comes from all the voxels in an imaging slice at the same time. Each echo contributes information for the entire image. That's why it's sensitive to patient motion, right? On CT, it only takes, 0.2 seconds to generate your images. But here, each echo contributes information to the entire image. So if your imaging sequence takes 5 minutes, but the patient only moved for 2 seconds of that 5 minutes, that's enough to mess up your image, okay? Because every individual echo has information for the whole image, for the entire image. Each phase encoding step requires sampling from a separate echo. Each echo, this is where K-space comes in, each echo corresponds to one line of K-space. Now we can have rectangular or square field of views, the phase encoding steps, number of voxels along the phase axis. We're sampling each echo, one line determines one line of data, one line of K-space. Each echo gives you one line of K-space. Generally, the number of echoes sampled equals the number of voxels along the phase encoding axis. That determines the number of lines of K-space. That determines the length of your imaging sequence. How many echoes do you need? It's usually determined by the number of phase encoding pixels in the phase encoding direction. So what's the advantage of a rectangular field of view versus a square field of view?
Fewer number of echoes?
Yeah. So if you have a rectangular field of view, it would be advantageous to place your phase encoding axis in this direction where you have less pixels. Then you require less echoes, and that shortens the imaging sequence. Okay? So K-space is the raw data matrix. Each line of data gives you one line of K-space. Generally, the number of echoes sampled is determined by the number of voxels along the phase encoding axis. That's the number of lines of K-space that you have to fill here. And once you've filled all your lines of K-space, you have enough data to generate your images. And this is why MRI is slower at acquiring images than CT, because we have to fill all of your lines of K-space from all of these separate echoes to be able to resolve in the phase encoding direction the three-dimensional information. Now, if you pictorially represent what these echoes look like as you're collecting the echoes, they don't look like an image at all. This is what K-space looks like if you take the information and just show it to you here. It's applying Fourier transformation to this data here that gives you the image. Okay, so when you look at pictures of K-space, that's why it looks very strange. It looks nothing like an image. Now, there's a couple other things we need to know about K-space. At the center of K-space, the center in here, the phase encoding gradient is very low. What that means is everything is more in phase when your phase encoding gradients are low, and your frequency encoding gradients also in here are very low. As you get towards the edges, the frequency and phase encoding gets higher. So we have more signal in the center of K-space because we have less dephasing, because the phase encoding gradient is low in the center of K-space. Also, your frequency encoding here is also, gradient is also less here. So things are more in phase, that gives you high signal. This corresponds to more image contrast. So the center of K-space is responsible for image contrast. The edges of K-space, as you get out towards the edges here, where the frequency encoding gradients are higher, towards the edges here, okay? Also the phase encoding gradients. The phase encoding gradients are higher towards the edges. Also the frequency encoding at the edges are higher. That means things are going to be more out of phase. Since they're more out of phase, your signal is less. But the advantage here at the edges of K-space is edge detail, and that provides spatial resolution. So the center of K-space gives you image contrast, the edges of K-space give you spatial resolution. Okay. Now, is there an intuitive way to understand this, that the center of K-space gives you image contrast, the edges give you image detail? So let's show you this. So K-space, we've said, kind of looks like this. If we just look at the middle of K-space and try to generate an image from that, we get nice image contrast, but not much image detail. If we go out and just use the peripheral portions of K-space and ignore the center of K-space and use that to generate, Fourier transform that to generate an image, now you kind of lose image contrast, but you have much better image detail here. You can see the edges of these structures, right? So the edges of K-space gives you this. Is there an intuitive way to understand why this is so? It's easy to understand why the center of K-space here gives you image contrast. So imagine I have fat here, right? So here's my, everything is in phase, right here. In the center of K-space, things are more in phase. Fat has a lot of signal compared to, let's say, the tissue around it that has less signal, right? So the signal from these homogeneous regions of tissue are all in phase. So there's a lot of signal here. So I'm going to get a lot of signal from fat, and I'm going to get a lot of signal here, although not as much as fat, a little bit less, but still it's very signal rich. And so imagine our phase encoding goes this way, and we're in the center of K-space, so there's not much dephasing from the phase encoding. So everything is in phase, everything is rich in signal. I get very nice contrast between the fat that is bright and the tissue surrounding it that is not as bright. So this gives me very nice image contrast. So that you can kind of understand why the center of K-space gives you image contrast. Okay? Why do the edges of K-space give you more image detail? So the explanation for this, by the way, was in this book. It's out of print, but it's like almost 20 years old. It's an excellent book from Vivian Lee, talking about cardiac MRI, where she talks about all of this stuff that's very interesting. So at the edges of K-space, your phase encoding gradients are higher, and that causes more dephasing. So if we look at adjacent rows here, right, at the very edges of K-space, they're 180 degrees out of phase. 180 degrees out of phase, 180 degrees out of phase. That means where you have homogeneous regions of tissue, like this fat and this soft tissue around it, the signals cancel. In this homogeneous region of tissue in the fat, these adjacent horizontal rows cancel. They cancel. Out here, they cancel. Here, they cancel. Where you have homogeneous tissue, that gives you very low signal, right? But what happens at the edge boundary? At the edge boundary, where there is difference between this and this, it doesn't completely cancel out the signal right at the edge. So the edges are seen where you have edge boundaries between different types of tissue. And that gives you spatial resolution. So going back to your image here, right, where we look at the center of K-space, we have lots of contrast, not much detail. When we go to the edges, this homogeneous area here, all the signal goes away. But right at the edges, right at the edge boundary, we get signal. And that provides the image detail, the spatial resolution. So that's an intuitive way to understand how the edges of K-space give you resolution and image detail at the edge boundaries. Okay. So why is that important? Well, when you're doing MRI angiography, you're giving a bolus of contrast. So the contrast goes through the vessels, and it's only there for about 10 seconds. but the imaging sequence may take 20 seconds, right? But you want to be able to image that contrast, that difference in contrast between the contrast in the vessel and the surrounding tissue while the contrast is going through. So how do we accentuate that? We accentuate that through what is called centric phase encoding, meaning we acquire the center of K space first when we're doing MR angiography. So as the contrast is going through the vessels, we acquire the center of K space when the contrast, that concentration of contrast is highest within the vessels. That accentuates that difference in contrast between the vascular structures and the non-vascular structures. So we will acquire this first, and then we will acquire the edges of K-space later, okay? And that accentuates the contrast of your images in MRI angiography for when you administer contrast. That is called centric phase encoding, right? And that's how we use this in MRI angiography, all right? All right, so we'll do the quiz next week. So just wanted to get through this. So that's the basics of MR physics. Any questions?